So here we are in Chapter 7 over processor control. And we're ready to talk about really how does a computer work? And so up to this point, where in Chapter 2 we talked about arithmetic of computers and basic logic. In Chapter 3 we talked about instruction set and how a program could be constructed from those instructions. We're at a place where we can provide some of the answers to the question of how are computers so fast? And so the theme of this chapter is internal operations of the microprocessor and some of the ways in which designers have improved their performance. And in particular, we'll talk about the RISC processors and how they're employed by all contemporary processors. And Chapter 7 gets into some advanced topics that I don't think are suitable for what I'm calling this beginner course, this introductory course. So I don't cover all of Chapter 7. Really, we have this introduction, and then we kind of hop over. There's a lot of really complex discussion about digital processors. And not only is this a little math intensive, but it's also, from an electrical engineering standpoint, going to be over most beginners' heads. And so at the beginning of this chapter, where they have a lot of diagrams on functional units and micro programming in detail and things like that, if you want to skim through that, I think that's great. But really, from a beginning standpoint, we want to talk about just the organization of the computer at the conceptual level, really that demonstrates how binary encoded instruction can be read and interpreted, and at a more practical level, some of the techniques employed to implement computers. And so, we've been talking about those CISICs and RISCs type organization, and that theme and variations philosophy of this text really helps us just kind of talk about that in a general way without hopefully getting into too many topics that are just going to be over your head anyway, which is not effective learning. And I apologize. I know some of you dislike the captions. I forgot to turn the captions on. I get requests for the captions. Of course, I know captions are very important. My apologies for not having those on in the beginning. So let's talk about computers as a hierarchy, right? A computer can be regarded as a hierarchical system with kind of these multiple levels of abstraction. And we can talk about the digital computer at kind of the same level of abstraction. And we saw in Chapter 3, when we talked about that low-level language layer, we saw a chart that looked like this. And so, really we have kind of these multiple layers. So you've got this application, right? And here are all the people that are interested in each layer and kind of where, you hear about these different titles, right? Or usages. This is where this kind of all comes in. So at this application level, right, this high-level language level, the computer is a device that performs a function. So it's a computer running a GPS mapping package that appears like a sat-nav device, right? And the user is interested at this level. The programmer is interested at this level. We have the computer scientist kind of, building the software that we need in order to make the system work. Then, at that high-level language area, more specifically, the computer is a machine that's executing that high-level language. And so all computers executing the same language are identical, right, in principle, and differ only in terms of performance, because at this point, high-level language not only means it's verbose and it's type safe, and we have a lot of things that we talk about with high-level languages that programmers learn, but we also do not have to think about the architecture of the computer. And gone are the days when we had to worry that our application wouldn't run on certain processors, or really that we had to think about the RAM at all, which is a soapbox I will get on about how software development today is full of bloat and mismanagement simply because our storage and our RAM has gotten so large that we no longer have to pay attention. Then we have our low-level language, right? So this is our programmer and our compiler, right? Our ISA lives at this level. And the computer is architecturally dependent, and the machine code is executed that will only run on one particular class of a computer. And this is where, so this person is still thinking about, is this a Core i7? Is this an i32? Right? What kind of system am I running on? What is the architecture? I do have to care. And so that's where we are when we talk about our assembly languages and our ARM languages. Then we have our microarchitecture in here, and with our micro program. And then this is where our computer designer and our engineer, this is where they are focused. So this level represents the physical organization of the computer in terms of our registers and our functional units and buses. And the microarchitecture may be unique to a particular instance of a microprocessor. So you might have two microprocessors that share the same low-level language, but different microarchitectures. And normally this level is not accessible by the end user. So modern programming logic does allow users to modify the microarchitecture of processors constructed from programmable logic. And really Chapter 7 is about this microarchitecture level. Then we get down into our circuit, right? Our gate layer. And the chart does point out the micro program is absent in some computers, right? But down here where we're getting into the circuit, this is our circuit designer and our device level where our scientists and engineers who actually build computers reside. And so these are the individual gates that determine the ultimate speed of the processor, and the device physics is the lowest level and is determined by the electronic properties of the material used to fabricate the gates. And so really this diagram illustrates these levels and those concerned with them, and it's an inverted pyramid representing the relative numbers of those involved with each level, because we have a very large number of computer users right up here at the top, at the highest part of the widest part of the pyramid, but relatively few people that are designing transistors right down here at this level. And so this microprogramming element might be absent if the low-level language is directly interpreted. So like in our RISC type processors, we may not need this extra little layer in here. But ultimately, this is how we can think of this computer as a hierarchical structure. So like I said, we're going to hop over the first part of this chapter that really gets into kind of circuit design and processor control of the digital microprocessor, and hop over to 7.2, which starts with RISC organization. And I want to begin with a gentle introduction to the organization of a simple RISC processor to make sure and provide a firm basis for later discussion of the features of RISC architecture that make them so amenable to pipelining. And we're going to talk about pipelining in more detail as well. So let's take a look at this figure 7.5, which presents the instruction encoding of a hypothetical processor that's not too dissimilar to commercial machines like ARM and MIPS. And we just made it a little bit simpler, again, going for easy. And we take a look here, the 6 most significant bits of the opcode are bits 31 through 26. And we can see that right down in here, right? 31 starting down here at this end, down to 26, which is right here. These define the instructions, and we have 1 bit for each instruction. So instructions are in the form of like 1 0 0 0 0 0 0 1 0 0 0, right? And so it's wasteful of bits, but it does allow us to simplify instruction encoding when we do it this way. And so the instructions that we see in here are put into these opcodes. So we have L for load, S for store, B for branch, J for jump. We have register to register, right? That's R to R. And X is reserved. And then we have bit 25, which is represented here by the pound sign, that hash sign right here. And this is our literal bit. And this indicates whether the second source register or the literal field is to be used in the instruction. And then we have bits 24 through 21, which are labeled in here as parameters. And these provide a parameter that can be used by any instruction. So, for example, if we need to define the type of register-to-register operation, like an add or a subtract, and then we need to define the condition in a branch operation, this is where we would do that. So the three register select fields that we can see down here, S1, S2, and D, in bits 20 to 12, these choose the registers that are going to take part in the current operation. And we've used 3-bit register fields permitting 8 registers, right? 2 to the third is 8. And then finally, the 12-bit field that we see in bits 11 through 0, which is labeled here by literal, provides a literal that can be used by instructions. And we saw how to use literals previously when we learned a little bit about ARM programming. And so the problem set at the end of this section here helps us kind of discuss the arrangement and suggest some alternatives. But from a very simple standpoint, this is the instruction format of our computer. So some of the typical operations that could be supported, right, we see those here in the code, that as we would be able to use these instructions that kind of cover different types of things you might want to do. So you might want to load something, store something, add something, branch, jump. And so hopefully you're at the point where you're starting to kind of see how this works, right? When we give these types of instructions, how are they read as an instruction? What is that format into our computer? Now over here in this figure 7.6, this multiport register file, this illustrates one of the most important components of what we have in modern processors. So this is what we call multiport memory, and this contains the general purpose register file. And so in a bus-based computer, you know, we've talked about buses lots of times. We know that these are what connect all of our components and peripherals and things together and allows data to move around the system. All right, these can implement any arbitrary number of registers simply by wiring them to a bus via some kind of suitable tri-state gate. However, what is needed in high-performance computers is an array of fast registers that can be accessed in parallel. And so really, remember I said we're going to talk about why are computers so fast, and we've been talking about computers in a very general, kind of simplistic kind of way to help you understand all of these different components. But in order to make a modern computer that actually operates at the speed of which we are familiar, right, we have these dedicated high-speed register files that are designed, that can be incorporated into our chips and kind of bought as standalone components, right? And these are called multi-port memories. And they have several access ports which can be used in parallel. And when we take a look at this figure, we can see that we have 3 address ports, which means that 3 registers can be addressed at the same time, and you can read 2 source registers simultaneously and write to the destination register. So with such a memory, with this component, you can implement an operation like add D S1 S2, and that adds the contents of register S1 to register S2 and puts the result in register D, and that all happens in one clock cycle. So as an example, we're now going to construct a processor by beginning with the basic structure and then adding features until we have a complete processor. So we're going to call this a flow-through processor because you can imagine an instruction flowing through it from the program counter on the left to the data memory on the right. And so this metaphor hopefully helps when we start to talk about pipelining. But take a look at this figure here in 7.7 that describes a simple processor that uses a multi-port memory as a register file. We've assumed a 3-register address structure, which is typical of RISC processors like MIPS and the ARM. And so this is an incomplete system, as it cannot yet implement literal operands or flow control, right? Our unconditional or conditional branches. It can't make subroutine calls or returns, but it can implement register to register load, or register to register and then load and store operations. So we're going to assume that initially the program counter contains the address of the next instruction to be executed, and this address is fed to the instruction memory and then back to the program counter via an incrementer where 4 is added to point to the next instruction, because we always have to remember that in ARM, our instructions are always going to be in 4-bit little blocks, right? Little bytes. I know that's hard. You don't want to think about it in like little bytes, like when you're talking about like nibbles, right? Never mind. I'm going to get us off on a tangent. All right, so we're going to assume a 32-bit instruction and a byte addressed mode. And so we would think about it, right? The instruction is fed to the instruction memory that provides the 32-bit opcode, and then it corresponds to the current instruction. All right, so let's take a look. And so we have our 3 register address fields that are sent to the register file to read source registers S1 and S2. And then the contents of those registers are fed to the ALU, where they're used to generate a value in a register to register operation. So that might be something like an add, an and, or a sub. And so they can be added together or create an effective address for use in a load and store operation. If the operation is register to register, then the result from the ALU is fed back to the register file via that multiplexer, and then we can write it in the destination port of the register file. If the operation is a load, the output of the ALU provides the effective address of the operand, which is used to access the operand from the data memory, which is fed via the multiplexer to the register file. If the operation is a store, then the S2 register output of the register field is fed to the data's memory data input. So we're going to note here that the store operation can't use the S2 source register as the address pointer in this particular implementation. And hopefully you can see why that's true when you look at this kind of diagram. And really, they're just kind of like flowcharts, right? We've got all these arrows. We can see the movement of the data to each one of our structures in our, we're calling our single cycle flow through processor. So let's take a look at a little fuller implementation of a load store processor. So this is the opcode format. And take a look at this here in the figure. We can see that there are 2 major additions over our previous diagram. So the first is the ability to deal with a literal in the opcode. And because this literal is only 12 bits wide, it has to be converted to 32 bits before being used by the ALU, which requires a sign extender block in the path between the literal field in the opcode and the ALU. It's also necessary to place a multiplexer at the input to the ALU to select between the S2 operand from the register file and the literal. The second addition that we can see here is the 4-way input multiplexer to the program counter, which selects between one of 3 paths in order to support branch and jump instructions. So you can see how we can kind of build onto this basic idea, slowly adding features until we get up to what we would probably consider to be a usable processor. So next we'll look at how we can examine the operation of the processor by looking at various classes of instruction and how those are executed. Hopefully we know at this point that the simplest instructions to execute are register-to-register operations. And if we take a look at figure 7.9, we can see how this works when we have this type of operation. So we've got some kind of successive figures here to walk through, and you can see the paths of information that are kind of grayed out and the functional units that are taking part or not taking part in the operation. So starting with our add operation as our opcode, if we had this register to register instruction, right, always in the format of like operation, and then we have our D, S1, S2, then all we need to do is feed the output of the two source registers from the register file to the ALU, and then route that result back to D as our destination, which then writes that input of the register file. So a multiplexer is required at the input of the ALU register file D port because information can be written into the register file from both the ALU and the data memory during a load operation. Note here that the program counter control block is not needed for this kind of load and store operation, and the PC input, right, PC plus floor, helps us point to that next instruction. So we can see we have our program counter. Here's our adder, right? We're always adding 4. We come into our program counter. We get our opcode. We can see how we have our D address S1, S2 into our register file. We read that through to the ALU. And when it performs its result, right, we can follow the path here. It goes through the memory multiplexer and then back around to our data port, which writes that back to the register file. So let's look at the data flow when we have our load and store operations rather than register to register. So in this figure here, the instruction LDRD, so we can see that instruction up here, with S1 and our literal L, is the address of the operand and is computed as the contents of source register S1, right, plus a literal L from the instruction. So this effective address from the ALU, so I take a look here, from the ALU, is used to look up the actual operand in memory, which is then routed through the memory multiplexer to the destination port of the register file where it's stored at address D. So we can kind of see how this is taking place to get back down here into our address, right, our D address, when we have a location that we need to look up. So again, not register to register, but loading and storing from memory. And then this figure shows us the flow of information when we want to execute a store. So in the previous we loaded, now we have the data to be stored, which needs to be fed into memory. So we're storing into S2, our S1 and our literal L. So the difference here we can see is the direction of data transfer. The memory address, S1 plus literal L, is calculated exactly as it was in our load, but the source operand from S2 in the register file is fed to the data input port of the memory. Right, and we can see this, right? Comes through into our data port. So at this point, we've only been looking at some simple operations, so let's talk about jump and branch operations. Remember, jump and branch both describe a means by which we change the instruction flow in the computer from a normal sequential flow to maybe go off and do something else in a subroutine or go perform another operation and then come back. So generally the term branch implies a jump to a location relative to the current value of the program counter, whereas a jump represents a jump to an absolute location. So a branch is invariably conditional. It takes place if a defined condition exists. So branching on 0, branching on carry. All right, we saw that when we did some of our ARM programming. But we're going to first look at a computed jump. So we can see that our opcode here is jump, S1, and our literal L. And then the relative condition branching, BEQ, L. But first we're going to take a look at this jump. So this unconditional jump operation executes the next instruction at S1, L, which means we have to get the contents of register S1 and add the offset of L from the instruction, and then basically jam that result in the program counter so that that's where we're going to go. So the 12-bit literal offset in the instruction is first sign extended to 32 bits. The contents of the source operand register S1 are read from the register file and added to the offset by the ALU. So do we see this as this moves through, right? We have literal L. Here's our jump. We move through the register file into the ALU. And then the result is sent to the program counter multiplexer and then to the program counter. So we come back, right? Here's our jump address into the PC multiplexer, back to the program counter, where the target address is now S1 plus L. So consequently, the next instruction that's going to be fetched from memory is wherever this address is, S1 plus L. So let's look at our conditional branch instructions so we can compare how these differ. So we have our BEQL, and in this case we use the program counter and the relative addressing. So the branch target address is the contents of the program counter plus the offset in instruction. So let's take a look at the figure to walk through this and we can kind of see how this is a little different. So we see the register file and the ALU and the memory data paths, right? All of these are grayed out. We're not using any of this over here. All we need to do is take the program counter and add the offset in the instruction. So all of that happens down here with our program counter and our multiplexer. So the offset is multiplied by 4 by shifting it 2 places to the left because the computer is a 32-bit machine, right? Addresses are separated by 4. And then this gives us our branching range. And then the program counter is incremented by 4 before that offset is added. So that's all we have to do. We implement a conditional branch, like branch on 0. All we have to do is use the Z bit from the computer's condition code register to determine whether the next address is the branch target address or the next address in the sequence. So in this figure, one of the bits in the PC multiplexer is wired to the Z bit, and that selects whether the branch is taken. And we can see that wiring down here. All right, hopefully you're sticking with me, and this is starting to make some sense as you watch and look at these different types of diagrams. And I hope the coloring helps, kind of graying out things that aren't being used in the current operation. And so now the next step is really to examine how the computer we have constructed here goes about translating machine-level opcodes into the actions that carry them out. So we have to look at what signals do we need in order to control the system. So first, we have to point out that we're looking at the basic principles only, and we've not included some of the other things that we've talked about, like interruptions and exception handling, or instruction and data memory control, right? So how instructions actually get into memory or how data gets into memory, right? So this is still kind of abstract, but we're wanting to understand how all of these different pieces of the microprocessor that we've talked about so far all kind of work together. And moreover, in a real computer, both the instruction and data memory are invariably not the computer's actual main memory system, but probably in its on-chip cache, right? We've talked a little bit about caches. Right now, we're just interested in an overview of the way in which an opcode is interpreted. So when we're looking at, adding control signals to the computer, there's a whole table of control signals and how they're used by different types of structures. And we can start to talk about, how many operands, what ALU it uses, how many, what control signal or PC multiplexers requires. We're not really too hung up on all of that information right now. What we want to look at is, how do we function with this instruction memory? And so let's take a look at this figure here, because we can look at the register file, which has two source operands, right? It reads ports S1 and S2. No control signals are going to be needed for these because the register file simply supplies the data being specified at the S1 and S2 address inputs. If the register file is not in use, then S1 and S2 outputs are ignored. However, a write control signal is required to write the data into the destination port D during a load operation or a register to register operation. And so we can take that data memory and that requires a single write signal, and when data is written into it during a store operation, right, it all works together. So when we think about control signals, right, 4 multiplexer control signals are necessary because there are 3 multiplexers, right? We can see that. 2 have 1 control signal, and the program counter multiplexer requires 2 control signals because it has to select one of 3 paths. And the instruction memory needs no control signals because it's fed an address from the program counter and it delivers the instruction. And remember, this all goes back to the clock. A single clock is needed to latch that new value onto the program counter at the end of a cycle and to latch data into the register file and data memory. So in this table here in 7.8, we have all of the signals required to implement each of the processor's instructions. So on the right, we can see the instructions and their definitions. And remember that the 4-bit ALU field can be used to specify one of 16 operations in a register-to-register operation, and it can be used to select one of 16 conditions in a conditional branch operation. So we can take a look at this table and kind of get an idea of the different instruction sets and how we would implement them. And if it helps, you can take some of these instructions, go back to our diagram that we've been looking at of our microcontroller and walk through each of the steps to see if you understand how things would move through the system. And so this figure here demonstrates the additional logic necessary to implement multiple conditional branches. So the Z, N, C, and V bits from the ALU are fed into a combinational logic block that uses the branch control from the instruction to select one of 16 branches. So we can see how those get fed through up into that branch control logic. So the outcome is used to control an AND gate, right? We see that here, our AND gate, whose output is 1 if both a branch operation has been selected and the chosen condition is true. Otherwise, the output is 0, which forces us to go to the next address. And so we force the program counter multiplexer to use the next program counter address rather than branch address whenever a branch is not taken. So this is essentially how we can control which address the program counter looks at and then which basically path we take. So the last thing I want to talk about in this section on controlling the computer is execution time, because we want to just briefly consider how long it takes to execute an instruction. In a flow-through single-cycle computer, it doesn't matter how long it takes to execute the average instruction. What matters is how long it takes to execute the longest or slowest instruction, because that determines the cycle time. Remember when we looked at our section on cycles and how one slow process can really slow down everything because it has to wait for that slowest process. So the longest or most complex instruction determines the cycle time, which means that less complex instructions have more time allocated to them than is actually necessary. So those kinds of complex instructions really kill performance. So the longest instruction is the load, because the opcode has to be read from memory, the register file accessed to calculate the effective address of the operands, the execution unit used to add the literal offset to the register, and the operand fetched from the data store, and then finally the operand must be stored in the register file. So if we take a look at this figure here, this demonstrates the information flow during a load operation with all of our information paths marked in the blue. And the sequence of actions and their times during a recycle would be, we have our program counter setup time. So from clock to program counter output stable. And then we would have our read instruction. So from the program counter stable to our opcode stable. And when I say stable, really what we're talking about is it's the end of the cycle. The data is there. It's not going to change. It's okay to access it. We have our read operand. So from opcode stable to operand stable. The time to add S1 and S2 to the ALU. From our address from the ALU stable to memory operand stable. And then from our memory multiplexer, the time that it takes to put that there, and then our data setup time of the destination operand in the register file. So you would add all of these values together, right? Our time for each step, and you would get the cycle time as a sum of all of those values. So this is the end of our first part of chapter 7. And so this part really looks at, the organization of the computer, our processor control, how things actually move around inside of here. Because again, what we're trying to answer is the question of how does it work and how is it so fast? So in the second part, we're going to start talking about the idea of pipelining and how instructions overlap to improve efficiency.